All right, so the other day we talked about congruent polygons, and congruent polygons were basically clones of one another. Anything that was a congruent figure was exactly the same in its angles and its shape and its size as another figure. But today we're talking about similar, and similar means something, well, similar, but slightly different than what congruent means. Similar figures are ones that could basically, if you want to use this metaphor, basically scale models of one another. So similar polygons have the same shape, but not necessarily the same size. So I like to think of similar figures like if you had a real life Ferrari and a tiny little scale model of a Ferrari that was exactly proportionally to size. The Matchbox car or the Hot Wheels or the little scale model of the Ferrari and the real Ferrari would be considered similar figures. And similar, the symbol for similar is the congruent sign without the equals in there. So you can just practice writing the little squiggly for similar. Similar polygons have the same shape but not necessarily the same size. All right, let's move on here. Okay, so they still have corresponding parts, just like congruent polygons did. So when figures are similar, their angles are corresponding, that means in the same spot, and congruent, but their sides are only similar, meaning that they are proportional. So if you said, in this case, that angle, not angle, triangle ABC was similar to triangle ABC, was similar to triangle EFG. You would have to, just like when we talked about the other day in congruent polygons, you would have to be able to know that angle A matched up and was corresponding and congruent to angle E. Angle B matched up and was corresponding and congruent to angle F. And angle C appears to be 90 degrees. So I'm just actually going to write in a 90-degree angle there. It matches up and it's corresponding and congruent to angle G. Right? So the same thing that we talked about yesterday is still true today. Right? So when describing similar polygons, the order of the vertices must be the same. This is exactly what I just said verbally in so many words. The order of the vertices still must be the same with congruent and corresponding angles, and the same thing is still true with the sides. Triangle ACB, and named it differently than I did. Triangle ACB is similar to triangle EGF. As long as you have C with G, B with F, you're still good to go. Okay, so you can know that angle A and angle E correspond and congruent. You can mark them up on your paper if you'd like. Angle C and angle G are corresponding and congruent still. Angle B and angle F are corresponding and congruent still. But the sides are merely proportional. The side AB corresponds to EF, but they are not the same size. They are not the same size. Line segment BC is corresponding, but is not the same size as FG. It is just similar. And AC is corresponding with EG, but is not the same size. It is congruent. So I do not want to write congruency marks on those particular. You can mark them on the angles, but not on the sides. Something like that. I'm going to take a second here, and I'm going to exit the PowerPoint just to highlight the difference between congruent figures and similar figures. So when you're talking about congruent figures, you're talking about perfect clones. So in Smart Notebook, I can hit the clone button, and right there I have made a perfect congruent figure. All sides are the same, and all angles are exactly the same. We can do the same thing with the yellow triangle here. Clone. Those are congruent figures. They are perfectly congruent to one another, and you can use the super fun congruent symbol to do that. If I can get the right pen up here. So obviously this little pale yellow parallelogram is congruent to that one, and this bright yellow triangle appears to be an obtuse isosceles triangle is perfectly congruent to that one. Let's use those exact same examples, but let's talk about similar figures. Similar figures if I choose to hit the clone button, would be not necessarily the same size. So what I'm going to do is just going to scale this one down. So you would say that this trapezoid is similar, not congruent, but similar, proportional to this one. It looks to be like a little mini-me of the previous triangle. But let's check out the angles. When I make this similar figure, the angle that's in the upper left-hand corner still matches up and is congruent. The angle that's in the right-hand corner still matches up and is congruent. The bottom right still matches up and is congruent. And the bottom left still matches up and is congruent. So there you have it. You can just visually see that the angles are still congruent, but the sides are merely proportional. And what does proportional mean? Well, we did a whole unit on proportions, but if you sort of forget, let's say if this side was 10 meters, and let's say this side was 5 meters, I'm going to use as simple of an example as I possibly can. You can know if this side up here was 12 meters, this side would have to be proportional by the same factor that these two are. So if you scale from the larger one to the smaller one, 10 to 5, the corresponding larger one that corresponds to 12 meters here must be the same factor. So if we cut 10 in half to equal its corresponding part, we're going to have to cut 12 in half to equal its corresponding part. There's proportional. You can probably tell already that it's going to be 6 meters there. They are proportional in side lengths anyway. Let's make a similar figure with this little yellow triangle here. So I'm going to clone it, and then I'm going to, in this one, I'm going to not scale it up, or scale it down, I'm going to scale it up. And let's check to see if the angles still match up here, even when I made it bigger. So here we go. Appears to have a match there. We appear to have a match here. And we appear to have a match there as well, right? So you would say that this figure is similar, not congruent, but similar, and you get to use just simply the squiggly sign to that one. And hopefully you get that point by now. All right, so let's move on. Like I said before, they have proportional sides. So when figures are similar, the corresponding sides are not congruent. Instead, they are proportional. So this means you can set up a proportion to solve for any missing side that you might have. So it looks like the same exact picture that we had before. If you have triangle ABC is similar to triangle EFG, you can know that sides that correspond are proportional to one another. This is almost the exact same example that I just used a second ago as far as the numbers were concerned. But I think you get the point here. All right, so let's go ahead and set up a proportion to do that. All right, set up a proportion and solve for the missing side x. Well, let me get out my pen. If I know that 10 corresponds with 5, I want to write a ratio on the one side of the proportion. The way 10 corresponds to 5 is the same way that this side that is called x should correspond to 6. All right, so a proportion is an equation of two equal ratios. If you remember how to solve these, you use a cross product to solve. So I'm going to go 5 times x on the one side is equal to 10 times 6 on the other side, which is 60. And I know you guys probably saw this and you're able to do this mentally. That's fine. You gave it the eyeball test. But just for a formality, x is going to be equal to 12 here, based on a cross product equation. This is not the only way that you could set up this equation, and we're going to talk about that when we go over the homework tomorrow. Right? Try this one on your own. Pause the video now and then do it with me. All right, so like I was just saying, there's a couple ways that you could set this up. There's actually, I think, 4 different ways, but these are the two main ones here. You could say that the way y corresponds to 4, the side zy corresponds to DC, so the measurement y must correspond to 4. I wrote that in a ratio. Is the same way that the larger side over here, xy, which is measured at 18, will correspond to 6. So there's my proportion, cross product. 6y is equal to 18 times 4, which is 72, I do believe. Then we're going to divide both sides by 6 and solve for y, and look at that, y is 12. One more time, okay? And then on the other side, if you solve this equation, it works out being the same exact thing. 18 times 4 is 72, and y times 6 is 6y once again, and spoiler alert, it comes out to the exact same thing. So as long as you set up your proportion appropriately, it's going to work out correctly. Right? So a useful thing of similar polygons is that it can be used to find the measure of an object indirectly without actually having to measure it by hand, without actually having to climb up a tree with some measuring tape and measuring exactly how tall the tree is. You can use a theorem of similar polygons to be able to solve for things indirectly. You're going to watch a short little video after this that talks about this guy named Thales, ancient Greek mathematician, who used this type of thing to be able to calculate the distances between ships at sea and how tall buildings were, etc. Okay. So measuring indirectly, a flagpole that stands 10 feet tall casts a shadow of 4 feet. If a tree standing near that flagpole casts a shadow of 7 feet, how tall is the tree? So here's a cool thing about the sun's rays. At any point in time, they're hitting all objects in the same relative latitude and longitude, of course, at the same exact angle, because the sun is in the same place in the sky for both this flagpole and the tree. So the shadows create similar figures. And I think you might have noticed this maybe when you were a little kid. You're walking with your parents, you might have noticed that if you were making shadows, their shadows were taller than yours were, or longer than yours were, because your parents were taller. So let's draw a picture to kind of articulate what's going on here. You've got a 10-foot tall flagpole, okay, casting a shadow of 4 feet. And you've got an X foot tall tree. We don't know how tall the tree is, that is casting a shadow of 7 feet. Drawing a picture to help you figure out any word problem is always really valuable. So here, let's draw our sun. If you notice, it is coming down at this exact angle for both of these figures, creating basically what you could call a similar figures here. And I did a bad job drawing those little rays right there, but you get the point. So let's actually use the highlighter. There we go. Something like that. And they're still not straight, but you get the point. All right, so let's set up a proportion. And then it doesn't set up a proportion for me. So I'm going to have to go ahead and do this. So the way the 10-foot object, aka the flagpole, corresponds to 4 feet is equal to the X foot tall object corresponding to a shadow that is 7 feet. Let's cross multiply and divide here. 10 times 7 is 70. It's equal to 4x, and this is not going to work out evenly, is it? Okay, so divide by 4. 4 is going to go into 70, say 15, 16, 17 times. 17 with a remainder of 2, so 17 and 1/2 feet. Check that, make sure I have that correct. All right, indirect measurement. Move on to the Thales video that is attached.